before maybe Nabil join us as a chair. So this is the first workshop on AI and data as part of the ACE network, which is Automatic Control Engineering Network. So this is basically to try to see the research work that is going on at the intersection of AI, learning data, and control theory and application. I'm very pleased and happy that we have really a rich program, and you will see it will span theoretical advances in the intersection field of AI learning and control, going to very exciting application like robotic, energy management systems, and brain application. So I'm really looking forward to hear the exciting talks from our speakers, and I would encourage you to interact with the speakers. Put your question in the chat. We will take them at the end of the presentations. And if you are happy to just unmute yourself and then ask your question, please do that. So I'm looking forward to the event, to your interactions with the speakers, and to the discussion we'll be having at the end with all of you. Okay. So the plan is to start with a very brief introduction on the AI and data grand challenge. And the plan is that Professor Nabil Of, who is the lead of that grand challenge, he will be presenting a couple of slides on the grand challenge, and then giving you a couple of dates, deadlines. So I'm just waiting for Nabil to connect with us, hopefully. And maybe meanwhile, so this is thanks to the efforts that this workshop is taking place to the ECR group as part of the ACE, who is led by Professor Fulvio Forni. I know he can't be with us at the end to give his remark. Maybe Fulvio, can you welcome the participant, give some welcoming to them, because we can't have you at the end for closing the workshop. Go ahead, Fulvio.
Thank you very much, Zehor, for giving me the opportunity to have a couple of words, and thank you everybody for attending and participating to this meeting. Those are new webinars that we are building as part of the UK ACE network. And so the purpose of this is to build an early career researcher community, to know each other and to start thinking more in terms of a control community. I think the UK country is very rich in that sense of a extended and very professional and strong community, but somehow it seemed like we are a bit disconnected. And so these events are the starting point as for early career researcher to build a stronger community within the ACE network. So thank you very much for being here.
So maybe without further ado, we can make start now. So I don't know, maybe Nabil, Dr. Of is having some issues to connect. He is not with us, but basically I can give a couple of words on the ACE network. So the ACE network really it started on January 2024 for a duration of 3 years. It was funded by the EPSRC, and really the idea is to bring together an interdisciplinary community to drive forward the UK research and innovation in control engineering, and hopefully we will build a community of control engineering in the UK. So we are hoping this network will address very global challenges.
Yo, I'm sorry to interrupt you. I think we don't see the slides anymore. We see your Google, some Google aid.
Yeah, it says it's Kostas Margellos screen, so maybe need to unshare.
Okay.
Yes, Kostas, I think we are seeing your screen.
And
you are muted.
I have some issues to stop sharing, apparently.
So let me
Um,
share again.
Okay, now we see back these slides. Thank you. Please go ahead, Zehor. Sorry for the interruption.
So, like the main objective of the ACE network, it's to address like global challenges and again to connect like researcher in the UK in control engineering. So, I think that the main points here were addressed in the previous. Some of them were addressed in the previous two workshops. So again, we try to have strong control engineering community, which like we are like very influential, but maybe less visible. So we'll try to continue to make a huge impact like on the community and the research, like the research going on in the field. Control engineering, like we need to admit that it's really key in many applications, industrial application, and we are very fortunate to have with us an industrial representative today to talk about where control and AI intervene within his company and the companies he has worked with. So we are not reaching out to the younger generation. So undergrad control engineering courses department are like disappearing, and this is why one of the key motivations that has led to this network. UK has a proud history of contribution to control engineering. We have to do more to support a future leader. So this is a 3 years program, and we are hoping like at the end of these 3 years, we have a stronger community, we have a stronger collaboration between control people in the UK. So we have like more than 200 members across various UK universities. We are very fortunate to have industrial partners again in all like the challenges or in all like the fields of the network, including manufacturing, healthcare, transport, automation, and IT. And the network has also secured support from key UK catapults. So those are our partner, like within the network. And so the outcomes, the main outcomes of the network, so are really to build an interdisciplinary research community, connect people, and engage with stakeholders and measure societal challenges. Research is key, and how we can plan for control engineering to contribute into really real life applications, societal challenges is one of the outcomes that are planned at hopefully at the end of this network. Trying to have a technology roadmap for short and long-term industrial needs with specific control engineering solution and game-changing recommendation for policymakers. This is a virtual center of excellence in automatic control to ensure a lasting legacy beyond the funding period. So we are hoping to like move forward with the main aim and objective of this network, even after the 3 years of fund, and have really a strong community. So trying to increase grant capture, multidisciplinary research, industrial collaboration, knowledge exchange, and long-term research collaboration, which are key to this network. So those are the grand challenges. We are here, the AI and data. We have heard 2 workshops previously within like the ACE network. We have one more next week, so keep tuned if you are interested to join us. So the AI and data, really, so this is a big theme. It might be a little bit misleading here, but we are really looking at the intersection of AI and data and control theory and control application, going from like signal identification and signal processing, the learning and the adaptive learning, reinforcement learning, and different types of learning controller, the safety of those learning learning controllers. And the third point, it's the computational intelligence in control, and how the data that we are having, like the increasing data in many applications, like healthcare application, how that can be used efficiently with classical control theory to achieve the control objective or the outcome. So those are the timeline for like the roadmap. In like, we are expecting to have a roadmap consultation workshop by June 2025, roadmap development and review by October, and basically sandpit workshops to have more opportunities to write joint grant together in early 2026, and hopefully have a bi-monthly online meetings within each grant challenge to address, I think, the feedback we will get from you, and then have more workshops. So this is the roadmap, and this is a brief overview on the ACE network and the AI and data theme. And without further ado, I think I will stop sharing, and I will introduce our speaker for the first session. So for those who joined late, so please do put your questions along the presentation in the chat, and I will be reading them at the end, and I will be monitoring the chat during the sessions. So our first speaker, I'm very glad to introduce our first speaker. So, can you see my screen on? Okay. So Kostas, can you please share your screen? So we have 3 sessions. We'll start with session 1 on research advances in control and AI. And the first speaker is Professor Kostas Margellos from the University of Oxford. He will talk about data-driven decision-making and safety certificate synthesis. So, Professor Kostas Margellos' research interests include optimization and control of complex insertion system with application to energy and transportation networks. And today he will talk about this intersection about learning and control theory. Thank you, Kostas, for being with us, and the floor is yours.
Thank you, Zehor. Thank you for having me here. Can you hear me and see the slides?
Yeah, we can.
Okay, perfect. So yeah, it is a great opportunity to participate in that event and give you a glimpse about what we have been doing recently. So my talk today kind of combines 2 main research interests that we have developed over the years, namely safety-based control. I started looking into that domain from my PhD time under different tools. Then I moved to data-driven optimization, and this word tries to link the 2. Before I go into the details and explain the different buzzwords in the title, let me just give credit to my PhD student, Luke Rickard, who has been the driving force behind those developments. And he also contributed in part to the slides that you will see today. So we recently submitted a manuscript to Automatica based on that talk. So you can find more technical details there. Because this is a short talk, about 20 minutes, I will try to give you a high-level overview of our approach to the problem. Okay, so let me motivate a bit what we mean by data-driven decision-making. So in our everyday life, we try to make decisions or perhaps come up with task schedules in operations that involve large-scale and perhaps safety-critical systems. What we typically do is we get information that we have from sensors. This could be, for example, data. And then we use this data, hopefully doing something intelligent with them to come up with decisions. So if we come from a control background, you immediately see a feedback loop forming there. The tricky bit here, the perplexity compared to traditional feedback loops, is that unlike traditional monolithic and perhaps simpler systems, we may not really know the underlying dynamics of the plant, of the process that we try to regulate. This might be because of uncertainty that affects that system, or it could even be because of incomplete knowledge or privacy issues in some parts of the system. Okay, so our goal is to come up with safety-based schedules that have prescribed safety properties, even if we don't really know the underlying system. Good. Since we try to build such decisions, such schedules on the basis of data, I would argue that those decisions are random. And very often this term has a bad connotation. But what we are doing in those cases is we try to accept the fact that those decisions are random and try to build trust. That means confidence on those random decisions. Okay, so with that pictorial example here, I try to illustrate that we make decisions based, for example, on a set of data. I call it a data bug. And sometimes those data could be representative of our process, of our underlying system. That means our decision is a valid one. This is what I mean by that tick. Another time, it could be that we are given a different data set, but still a good one. But we can also have misrepresentative data for our process. And this may lead to erroneous schedules, to erroneous decisions. So under this regime, where we operate on the basis of the data that we've seen, coming up with valid schedules all the time, so always, is too good to be true. So we relax a bit our requirements. And our thought process here is that we are trying to come up with good enough decisions for most of the data bugs that we are provided with. So there will be some notion of probability appearing here, capturing our likelihood, our probability of trusting our decision. Or a different way of seeing this is how can we quantify the risk that is associated with a given schedule that we are making on the basis of data. So this is our strategy. And in particular, we follow that these principles to solve verification problems and accompany a verification outcome with formal guarantees. Okay? So let me explain this in a bit more detail. We will consider closed loop systems. That means that you have some system which is perhaps unknown. You close the loop through some fixed controller structure. It could be your favorite controller. It could be an LQR controller. It could be an MPC controller. And then we are trying to say something about the properties of the closed loop system. Okay? Again, I would like to emphasize that we may not know the actual dynamics, so we don't have a closed form expression of the system. And the only information that we may have available is a bunch of signatures of that system. This could be thought of as closed loop trajectories. And I will refer to those as data. This is the data for the system that I'm considering. Okay? So within this regime, we will try to verify different system properties. We have applied our methodology to safety problems. So you are trying to say whether a system will evolve within a safe portion of the state space without entering an unsafe part. Or reachability problems. You may want to have a finite horizon reachability problem where you reach a certain goal set. Or composition of the two. You may want to reach a target while avoiding an unsafe set. And even more complex properties like sequential reach problems and so on and so forth. So in the rest of the talk, I will talk about safety problems, but you can replace safety with any of those specifications. We have attempted to apply this methodology to all those problems. Good. Okay, so let me explain the process that we followed. We try to verify whether a given property, for example, a safe property for our system holds. And to do this, we try to learn a certificate by means of data. We can think about certificates in the simplest case if you come from stability as a Lyapunov function. If you are into safety, this could be barrier functions or even more complex functions that encode the specification of interest. Okay? So this is the learning part of the process, learning from data. But the most interesting part that we focused on is how we can generalize the properties of a learned certificate when it comes to unseen trajectories, unseen data from our closed loop system. Okay? So once you have a certificate in place, what can you say about how likely it is that this certificate will remain a valid one, or in other words, that your system will remain safe when it comes into a new realization, a new signature of your system? Okay, good. If we didn't have data and we wanted to have a robust statement, one way of saying this is that we are looking for a function v, I hope you can see my cursor, that satisfies certain conditions. These are denoted by psi related to the property of our interest. Again, thinking about a barrier function, we may want our v, for example, to satisfy certain positivity conditions. These are deterministic conditions that are denoted by this generic object psi d. Or it could be conditions that depend on the system, like, for example, a non-increase condition along the trajectories of our system. I call this psi s. And psi s is a function of delta delta plays the role here of a data point. That means a trajectory of our system. So if you see some condition depending on data, it means that is a trajectory dependent condition for our system. Okay? And all the properties that I can describe before could be encoded by specific properties of those functions psi. Okay? So if you find some function v that satisfies those conditions, we say that this function v would be a certificate for our property, and we in turn denote our property with phi. So ideally, we'd like to satisfy a given property for all trajectories of our system, so a universal satisfaction of the property. As I tried to argue with this pictorial cartoon before, this is too good to be true. So we rather want to satisfy this with some probability. So we will relax a bit our requirement. We will learn something on the basis of data and try to guarantee that a given property phi, for example, safety, reachability, reach avoid, and so on, is satisfied with a prescribed probability. Okay. So to do this, we try to view this problem under a statistical learning theoretic lens, and in particular, we use the so-called probably approximately correct learning framework. I will explain the different terms in that possibly ugly name. Okay. So we zoomed out a bit, and we tried to view the learning of a certificate problem as a sort of classification problem. So assume that you have a certain target set that you want to learn, that you want to approximate. It's a known. And for us, this target set is a pool of all system trajectories. We don't know the set, but we make a guess. And our guess is called the hypothesis of what this target is. This hypothesis is, for example, a certificate that we learn classifying trajectories are safe. So it's a portion of our trajectories that are classified as safe by a learned certificate. Clearly, the hypothesis and the target will not be the same. And we want to accompany our hypothesis with some guarantees on the likelihood, on the probability of resulting in an invalid certificate, or in other words, invalidating our property. That means that our system is unsafe. Okay? So if we are able to address our problem, that means the hypothesis and approximation of the target at that abstract level, then we can go back using this assignment that I have here to say something about the validity of our learned certificate. Okay? So this is what I will try to do in the next slides. I will try to zoom out. I will talk about a generic learning problem where we want to approximate a target set by means of a hypothesis which is based on data, and then return to the certificate problem. Okay? Good. So to do this, I will use this textbook-like example for statistical learning, where the target set here, for the sake of that example, is an axis-aligned rectangle. Assume that you don't really know the rectangle. That means the solid line object that you see there, but you are only given some samples, that is the dots, that fall inside the target. So you are given a labeled data set, but not the set itself. Okay? But if I am given points that belong to a set, and I know that I'm looking for an axis-aligned rectangle, a natural choice would be to take my hypothesis, my estimate of that target set, to be the smallest axis-aligned rectangle that contains the sample. So this is the dust line object that you see here. Okay? So if this is my approximation of the target, it's very unlikely that I get the true set. So I'm accumulating an error. And the way to describe the error would be in the form of the probability mass that falls inside the green shaded area that I try to illustrate in that cartoonist figure. Okay? So this area is in some way a misclassification error. So it's the probability that my hypothesis, that means my estimate of the target based on m samples, differs from the target. So the probability of something bad happening. And we would like this misclassification to be small, for example, smaller than a given risk level epsilon. Okay? So that green statement here models something good. It means that something bad happening is small, which is a good assessment for our hypothesis, for our approximation of the target. Good. Since our hypothesis is based on samples, so we learned that set on the basis of some samples, this is a random variable on its own. And as a result, this green probability is a random variable as well. So it's too good to be true to expect that we can guarantee this for all data sets that we are provided. There can always be, again, misrepresentative data bugs for which this error in probability is much higher than epsilon. Okay? That means that we have to have some probability confidence on our green statement. So all this green statement, which involves some probability, is itself satisfied with some confidence. So the problem that we would like to address in that case is for a given confidence that someone is providing, let's say 1 minus beta, we want to make sure that the green statement is satisfied. That means our misclassification error is small. It meets a given threshold epsilon. Good. Okay, so the goal here is to determine that risk level. In practice, someone would give us the level of trust that they would be happy with according to their safety critical application. For example, they would like 1 minus beta to be a number very close to 1, so that we are very confident about the statement that we are making. And we would like to determine epsilon. That means to determine the risk associated with the learned decision or the risk associated with the learned certificate, if we map to the certificate synthesis problem. Okay? So this is the problem that we try to address, how to determine such an epsilon. Just to give you a flavor of what goes under the hood, one sufficient condition to be able to determine useful epsilons is the existence of a compression set for the learning algorithm. I will not give you a formal definition of this, but a pictorial one, which is very close to the formal. So assume that you have a learning process. You feed it with samples, data points, let's say delta 1 up to delta m. And this process, this algorithm produces a hypothesis, HM. Okay? Assume that I solve exactly the same learning approach, the same learning process, but this time I feed my algorithm with fewer samples, only D of those samples, and produce another hypothesis, which indicated here by HD to emphasize the fact that this is based on fewer samples. If it so happens that there exists a subset of my data with cardinality D smaller than all the data that I have at hand, but the hypothesis that I produce is the same with the hypothesis that I would get if I were using all the data points, then I'm saying that my data set and my algorithm admits a compression set. Okay? So only some of the data is important. If you think about the axis-aligned rectangle example, that would be the data points that fall on the boundaries of the rectangle. All other ones are in some way redundant, but they're useful because they build as our confidence on the decision. Good. So if this condition is met, so if we know that a subset of the data is important, then we can provide an answer to our problem. So the problem becomes a theory, and we can get concrete expressions for that risk level epsilon. Okay? Those expressions depend on solving certain polynomial equations. I will not illustrate the equations here because I don't think it's meaningful, but I would rather spend some time explaining the quantities on which this epsilon, this risk level depends on. So this epsilon depends linearly on 1 over m. That means the more data points we are provided, m denotes the number of data points, the smaller epsilon is. That means the better our approximation accuracy, which is also intuitively true. Another important property of epsilon is that it scales logarithmically with respect to the confidence, that is the trust on our decision. So if you want to make 1 minus beta to be very close to 1, what this says is that this is cheap. The price that you are paying in terms of the dependence of epsilon on the confidence is only marginal. And the final quantity on which this epsilon, this risk level depends on, is this cardinality of the compression set of the important samples that we have in our population of samples. So roughly speaking, this suggests that the smaller the cardinality of a compression, the better the guarantees. And effectively, this says, in other words, that try to avoid trivial compression sets. Someone could say that I can take as a compression set the entire data set. This would be valid, but in that case, the risk level epsilons that we will identify would be really poor. We would be providing correct, but not useful statements. For example, claiming that our misclassification probability is smaller even up to 1, which is always the case. Okay? So to get sharp characterizations of the risk level, you'd better find small in cardinality compression sets. Okay, so having that theorem in mind, so a recipe under which we can provide guarantees on a learned decision, on a hypothesis, we could go back to our certificate synthesis problem and do the translation, the variable assignment that we had before between hypothesis, targets, and misclassifications. In a certificate synthesis problem, we can take our hypothesis to be this function, for example, a Lyapunov function, a barrier function, a generic certificate that classifies trajectories are safe or unsafe. So it could be a level set of our function. Then the probability of misclassification, the error between a target and a hypothesis, boils down to be just the probability of being unsafe, or in other words, the probability that your certificate becomes invalid. In other words, we can use the theorem that I just illustrated to bound the probability of a property dissatisfaction. For example, the probability of being unsafe can be now bounded by a given risk level epsilon that we are able to quantify if a compression set for our algorithm exists. Okay? So it seems that we move the problem somewhere else. If we want to construct certificates and accompany those certificates with prescribed risk levels, because these are random, we need to be able, first of all, to compute them on the basis of data. And a second point is that we need to compute compression sets that are non-trivial so that we can quantify those epsilons. Okay? So I will try to spend my last minutes explaining how we did this, what was the algorithm to compute the certificate that we followed, and how we computed compression sets for that case. So the way to compute certificate here was rather simple. We parameterized certificates by means of neural networks, of the self-neural network. So the parameterization of our certificate boils down to be the three parameters of a neural network. And to train a neural network based on some data, some signatures of our system, we had to define an appropriate loss function. So the loss function that we consider here encoded the violation of the different certificates conditions. So for every certificate, we need certain conditions to be met. Think, for example, about Lyapunov functions or barrier functions. You have some non-increased conditions and so on. Assume that you have some condition residuals, and we lift them up in a loss function through penalty terms. So we have a soft version of those conditions. This is the loss function that we try to minimize when we train our network. So one way of thinking about this training process, inspired by physics-informed neural network, this is a safety-informed neural network, whether we are trying to come up with parameters that minimize the loss function that we define, but because of the choice of the loss function, if this loss is 0, for example, we are meeting in a hard way our certificate's conditions. Okay, good. So this process involves minimizing some loss function, where the parameterization of certificate depends on the neural network that we are using. Good. This is a difficult problem to minimize that loss, and the difficulty comes because for arbitrary neural networks, this process involves a non-convex landscape. So we have to solve a non-convex optimization problem and find the best set of parameters that minimize our loss. And more than that, for this non-convex optimization problem, we need to accompany our optimal parameter vector or the converged parameter vector of that process with a non-trivial compression set that we should be able to calculate its cardinality. Okay? So look, my PhD student tried to address both problems in one shot to develop an algorithm that actually goes to some local optimum of the non-convex landscape, and at the same time, as a byproduct, calculates that important cardinality of the data compression. Okay? So the algorithm is rather lengthy. You can find the pseudocode in the paper, but I tried to illustrate it by means of a cartoon, just that I highlight on a smaller example, on a pictorial example, the basic principles of the algorithm. So my cartoon involves a penguin skiing along some mountains. So those mountains, the epigraph of those mountains corresponds to the non-convex landscape that we want to optimize when we train a neural network. So it could be thought of as the loss function. And the horizontal axis is our parameter space. So we try to find potentially some local optimum in this non-convex landscape. Okay, good. So this skiing problem that the penguin is doing is a bit bizarre. So the penguin, when it starts at a particular point, does some sort of subgradient descent scheme with a fixed step size. So it can only go downhill. It cannot go uphill a mountain. But every now and then it can jump, according to a given rule that we have at hand. I will explain this in a second. Okay? Let me just say that this is some inexact subgradient scheme, because ideally we would like to minimize the worst case loss, worst case according to the data that we have. That means we need to stay on top of the mountains. But if the penguin follows a gradient, it will quickly go down the hill. Okay. What I try to illustrate here is with the blue dots, you see some gradient steps that the penguin is following. So it goes down the right slope of a given mountain, whereas the green dots illustrate the worst case exact subgradient at a given parameter point. Okay? So if you can see my cursor, at this point here, there exists some other mountain slope whose green dot, the green subgradient, would be the exact one. So ideally, our penguin should be at the green points. But because we are following inexact subgradients, we just follow the blue trajectory. Okay? However, at that particular blue point, so when we reach very down that hill, the dot product between the true and the approximate subgradient that we are following becomes negative. Pictorially, this means that at that particular parameter value, there exists a slope, the one up here with blue, that has a gradient opposite the opposite direction compared to the ones that the penguin has explored. Okay?
Sorry to interrupt, Kostas, 2 minutes.
Yeah. I'm reaching the end. So at that point, the penguin is allowed to jump and follow the exact gradient at that point. And that means we pick up a second slope, a second mountain that we investigate, that we ski, and we increase the cardinality of our compression set by 1. So we start exploring through this regime our non-convex domain, while keeping a bag with the important samples that we have been following throughout this process that plays the role of our compression set. The process still follows the same regime. So at some point, the penguin will investigate yet another mountain. It will allow it to be jump again. And then after some oscillations, it will converge to that local minimum in that pictorial example. So this will be the returned parameter vector if we apply the algorithm to that penguin's problem. And the number of jumps that the penguin made, so the number of mountains that we explored, has to do with the cardinality of the compression sets, the samples that were important. So what we liked about this algorithm is that not only it allows us to minimize a non-convex loss function, but it also allowed us to compute this important cardinality that affects our risk, the risk with which we accompany our certificates, in a non-convex optimization setting, which is an interesting observation on its own. It's very rare that you can compute meaningful compression sets for non-convex optimization problems. Good. So this is the general recipe of the algorithm. It's an inexact subgradient descent scheme with jumps. Good. Okay, let me show you some application of that algorithm to an example. For the sake of illustration, this was a 2D problem. So we would like to start from an initial set. This is denoted by the blue rectangle. And we want to stay in a given operation domain, the black rectangle, while avoiding an unsafe set, which is the red one. The surface that you see is the surface of a certificate that we learned by means of a neural network that was fed with 1,000 different signatures of our system. And for that certificate, we can say that the probability of misclassifying a point as unsafe is at most 4%. Okay? And we have confidence, we have trust in that statement about how good our certificate is, about the probability of being unsafe, which is very close to 1. It's 1 minus 10 to the minus 5, okay? According to the expression that we have for epsilon in relationship to our confidence. Okay? So here, the level set of that certificate, which is denoted by dashed line, is kind of a separator between the safe or unsafe classification that the certificate is doing. Good. So we have benchmarked this approach to different problems that scale up to 8 dimensions so far. For all those, we get meaningful certificates and also risk levels associated to those certificates. So it is as if we accompany neural networks that learn certificates with prescribed guarantees. And the guarantees are of the order of 5 to 10%, which we believe it's very relevant for applications. Okay? And as I argued at the beginning, we also applied it to different specifications, reachability, reach avoid, sequential reach avoid problems, and so on and so forth. Okay, let me sum up. So I tried to give you a glimpse about the way that we view data-driven synthesis of certificates. We have neural networks in the loop to learn those certificates, but use theoretically solid tools from statistical learning in order to accompany those certificates with guarantees about their validity to unseen data points. While another byproduct of our analysis was some exploitation algorithm to investigate non-convex landscapes and at the same time build compression sets for our learning algorithm. Okay, in terms of vistas, what we are doing currently, we are trying to extend this approach not just to certificate synthesis for closed-loop systems, but we try to co-design controllers and certificates at the same time. This is a more difficult problem. And the second direction that we're looking into is how we can extend this certificate synthesis problem to multi-agent systems, where the different agents have access to different data sets. So we don't have a global pool of data that all agents in our population can use, but we try to synthesize a global certificate having access only to private data sets without exchanging the data. Because we believe that this is also practically relevant in large-scale applications where the different decision-making entities have access to separate data pools. Good. So I will stop here. I will be happy to take any questions.
Thank you, Kostas, for this nice presentation. We don't have questions in the chat. Any questions for Kostas? So please put it in the chat or you can ask the question directly. I have one, Kostas. So what do you think, like, how computationally intensive is your algorithm to solve the non-convex problem? And what do you think on its scalability when you move to multi-agent? This is very important, like, point when you move to multi-agent.
So it's a non-convex problem.
Yeah.
We follow some inexact subgradient scheme, where the subgradient refers to the subgradient of the loss function that we define for our neural network. So one difficulty is to calculate a subgradient. Okay, if we consider this as a straightforward task for reasonable loss functions, because our loss functions depend on our specifications. So the more involved the specification, perhaps the more involved the loss function. But if a subgradient is computed, then computationally, it's a simple iteration. We don't really solve an optimization problem. We just follow the subgradient with a fixed step size. And we jump every now and then. If there are multiple agents, then one would try to parallelize this task. And what I would have in mind, but this is to be explored, is to have some sort of parallelizable projected subgradient step that the different agents are solving together with some consensus protocol on the top.
Thanks, Kostas. Yeah, Jack.
Thanks, Kostas, for a very nice talk. One question, how does the quality of the minimum that you find affect the theoretical results? I mean, I'm not so familiar, but naively, it seems like the more important thing was that both algorithms return the same solution for different input sets, but it wasn't clear how the quality of that solution kind of affects the overall result.
That's a good point. So these are, so if you think about this probabilistic statement with which we accompany our solution, this refers to the probability that a property stops being satisfied, right? Or a certificate becomes invalid. So it's more like a feasibility statement rather than an optimality statement that you are mentioning. So the answer to your question is it doesn't, which means that those guarantees are kind of detangled from how good your optimum is. But at the same time, there is a danger that you may get stuck to very poor local optima in that function, and we don't have direct control into this. The way to counteract this, so what we did in our algorithm is we incorporated a data discarding mechanism. So if we believe that we have outliers, or if we are not happy with the value of our optimum, we start discarding data. This improves our cost, but at the same time, it increases the cardinality of our compression set. That means our risk level. But you can think of this as a knob that you can trade optimality to risk statements.
Okay,
So if
yeah,
we encounter poor risk level, if we encounter poor optima, we start discarding data and increase the epsilon.
I see. Yeah, thanks.
So there is an outer algorithm that I did not present on this to account for that.
Thanks.
a lot, Kostas. So we'll move to the next. So you will have the chance maybe to, if you have any further questions for Kostas, we'll have an open discussion at the end. So feel free to interact with our speakers at the end. So
I will stop sharing it.
yeah, should we take it maybe in the open discussion, Kostas?
Yeah, yeah.
To move, yeah. Mohammed, we will address your question at the end in the open discussion. Okay, thanks, Kostas. Our second speaker is Dr. Morgan Jones from the University of Sheffield. So Morgan will be talking about application of set approximation in AI and engineering. So he is actually currently an assistant professor with the Department of Computer Science. He is an assistant professor with the Department of Automatic Control and Systems Engineering at the University of Sheffield. And his research, it's mainly on estimation of reachable sets, attractors, and region of attraction for nonlinear ODE. He has also an interest in extended dynamic programming framework into non-separable cost functions. So the floor is yours, Morgan.
Thanks very much for the introduction, Zehor. Hopefully everyone can hear me and see my slides. So today I'm going to be talking about set approximation. Most of the technical results can be found in this paper that was published late last year. And in this talk, I'm mostly going to be talking about approximation in the volume metric, not the Hausdorff metric. To motivate these type of set approximation problems, I'm going to start with a practical problem of path planning and obstacle avoidance. So you can imagine some sort of robot in a warehouse factory that has scanners and sensors that's able to collect data. And using these data, it can identify obstacles and it needs to plan a path from A to B. And there's many algorithms that can do this type of planning, such as A-star search. But as we'll see, there is a slight reformulation that needs to happen to be able to use these algorithms. So these algorithms that have been around for quite a long time now do not inherently take into account the shape of the robot or the agent that's moving through the environment. So one common approach to do this is to so-called transform the problem into a space called the configuration space or the C space. Here's a diagram that shows how to do this when you have simple shapes. How you transform it to C shape is you need to enlarge the obstacles in such a way that you no longer need to consider the shape of the robot. The robot can just be considered as a discrete point, and then you can run any classical algorithm like A-star search. And how we enlarge the shape of the obstacles is that you need to take the Minkowski sum between the shape of the robot and the shape of the obstacles. So to transform into C space, there's really two problems you need to solve here. The first problem is that once your robot has scanned the environment and collected point cloud data, so these are data samples that live in some Euclidean space. If this is a path planning problem in real life, the Euclidean space would be three-dimensional, but they are path planning problems in higher dimension. And you need to construct some sort of set that represents the surface in which these points have been sampled from. So this is reconstructing the surface of the obstacles you would like to avoid. So this diagram shows the algorithm that we're going to talk about that has done this for a famous benchmark called the Stanford Bunny, where we can see the point cloud data set as these discrete points. And the red area is going to be a polynomial sublevel set that sort of encapsulates these points and represents the surface of an object. The second operation you need to compute is the Minkowski sum. So this is the Minkowski sum, where it's a sort of an addition of two sets. And how you compute the Minkowski sum is that you take each element from the individual sets and add them together. So these sets would be the shape of the robot and the shape of the obstacle. And for convex, well-behaved sets, there are many algorithms to compute the Minkowski sum. So here I'm adding a triangle and a circle, and the green area on the right is the Minkowski sum. And that's how you enlarge the obstacle that you need to avoid. But for more complicated shapes, like this bunny shape, it becomes more and more computationally challenging to compute these type of Minkowski sums. So our approach to solving this type of problem is to represent everything as a polynomial sublevel set. So we'll approximate these discrete points by a polynomial sublevel set, and then we'll add two polynomial sublevel sets together under the Minkowski sum addition, and also approximate this by a polynomial sublevel set. And then we can easily add these as constraints to a path planning problem and solve the problem of getting from A to B. So why sublevel sets? Because firstly, they can easily be added as constraints to an optimization problem. They appear as inequality constraints. And this type of set approximation problem actually appears in a lot of areas of control theory. So this is a sublevel set. It's all of the points such that some function that maps from Rn to the scalars is less than a scalar value. Here is gamma. And sublevel sets appear in stability analysis. So the sublevel set of a Lyapunov function is the stable region. So that's the van der Pol oscillator. The sublevel set of a value function can give the forward and backward reachable sets of a nonlinear system. We typically represent input and state constraints as sublevel sets, as well as uncertainties. And also in CAD/CAM modeling, some methods represent the surface as a sublevel set. But the method I'm looking at in particular is we're trying to represent the surface as a polynomial sublevel set. So sublevel set approximation is very much related to this following question. If two functions are close together under some approximation, does that mean that their sublevel sets are close together under some approximation? And it seems to be a lot of factors that might influence your answer here, such as what is the value of gamma that defines your sublevel set? What is the domain that you're taking the points over? Do you define the sublevel set using strict or non-strict inequalities? What type of function approximation do you mean? And what type of sublevel set approximation? Because there's many metrics that show when sets are close together or when functions are close together. And are there any particular properties of V and J you would need such that their sublevel sets are close together? So the work tries to answer this question or give some conditions of instances when two functions are close together, their sublevel sets become close together. So for this talk, we're just going to consider the volume metric, and this is the Lebesgue integral of the non-overlapping area of two sets. So if you have two sets, A and B, in this diagram are circles, they do not overlap in the red region, and then if you integrate over this region, this gives you a metric of how dissimilar the sets are, and we call this metric the volume metric. So there's plenty of counterexamples of functions that are close together where their sublevel sets are very distant. So here we have a function v, that's an indicator function, and another function j, which is exactly v, but it's perturbed by a fraction 1 over d. And as d tends to infinity, this perturbation gets smaller and smaller. So j does tend to v. But j, for any value of d, j takes values that are always strictly less than 1. So the sublevel set of the j function is the entire domain, whereas the sublevel set of the v function is a subset of the entire domain. It's all the points between 1 and 2. So clearly the sublevel sets are very distant, no matter how large you select the value of d. And there's plenty of other counterexamples of functions that are close together with distant sublevel sets on the archive version of the paper. But this shows that even in the L infinity norm, you can get functions that are close together, but their sublevel sets are distant. So we propose this theoretical result of how to do sublevel set approximation. And if you have the condition that J is uniformly less than or equal to the function that you're trying to approximate the sublevel set of, and you also tend to it in the L1 norm, then the non-strict sublevel set will tend to each other in the volumetric as your approximation gets better and better. And this theorem informs us how we should computationally go about approximating sublevel sets. So if you're given some set X, the first step is that you should try to write this set in terms of a sublevel set. And sometimes you don't always need to know what the function V is that characterizes the set X, because it could be of maybe a converse Lyapunov function that you know exists, but you don't have a formula for it. And then the next step would be to try and uniformly approximate this function V from below, and then you'll know that the sublevel set should also converge. So this formulates an optimization problem where we're constraining this function J to be uniformly less than or equal to another function V from below, and also approximating the L1 norm. Because of the constraint, you can remove the absolute value, and there's only the only decision variable of this problem is JD. So you can reformulate the problem into a linear programming problem, because now your decision variable only appears linearly in the objective and the constraints. The issue is that this has infinite constraints, because you need to enforce that J is less than or equal to this function V for all X in the domain, and there could be uncountably many X. But luckily, there's many computational tools that can enforce these constraints through tightening the problem, and you can still get this convergence in sublevel sets as the degree tends to infinity. So in my work, I use sum of squares programming. I'm not going to discuss in detail in this talk. We'll just consider it as a black box where we can put this function approximation problem into it, and it can give us a solution. And we can, there's cases where you know a formula for V, but it might not necessarily be polynomial, but you can still use sum of squares programming to enforce this constraint of being uniformly less than or equal to V. And there's cases where V is implicitly known, like a converse Lyapunov function, and you have no formula, yet there's still ways to enforce this constraint. And even though we tighten to a sum of squares optimization problem, you can still prove convergence in the sublevel sets. So the paper looked at several sets that we would like to approximate by a single polynomial sublevel set, including intersections of semi-algebraic sets, unions of semi-algebraic sets, Minkowski sums, which is important to our application. And each of these sets we write as a sublevel set of a single function. So here, the Minkowski sum between two sublevel sets involves an infimum involving both of the functions. So it's like an optimization problem inside. That's why the Minkowski sum is hard to compute. And the other interesting function is that approximating the discrete points, which is the indicator function, by a polynomial from below to approximate the point cloud data set. So here's some numerical examples. So approximating this indicator function from below by a polynomial, if you get given some point cloud data set. So this is another benchmark called the Utah teapot. This is a polynomial degree 20 representation sublevel set of this point cloud data set. It does okay, but it kind of misses some topology, like there's a hole in the handle here, which isn't represented by the polynomial. So there's some improvement can still be made. I have experimented with clustering the data set and approximating the clusters by polynomials, and it does improve the topology, but then you don't get a single polynomial sublevel set, you get a union of polynomial sublevel sets. And you can also do other things. You can add shape constraints. So this is the optimization problem we're solving. We're approximating V in the L1 norm, but you can also enforce the sublevel set that you get to be symmetric, connected, or convex. So convexity is quite easy to enforce. You just need to enforce that the Hessian of this J function is positive, which can be enforced using sum of squares programming. So here's a numerical example of me enforcing different shape constraints while learning a point cloud data set. So I took this picture of a packet of crisps on my phone and extracted the point cloud data set from the JPEG, and I fitted with no shape constraints, and there were some holes in the polynomial, and that's because there were some holes between the point cloud data points. But then I could enforce symmetry, and this made the holes symmetric. I could enforce it to be star connected, and this eliminated all of the holes. And I could also enforce it to be convex if I want. For the Minkowski sum approximation, I needed to approximate this more complicated function that involved a infimum, but the paper gives you the sum of squares optimization problem to do this. And this is a path planning example where the robot is just of a simple shape. It's a circular shape, but the obstacles are different, more complicated shapes, like we have a star shape right here and rectangles. And the red area is the Minkowski sum between the circular shape and the different obstacles using this set approximation approach. And you can see that the obstacles are enlarged, and then you can run any path planning algorithm you want to avoid the obstacles in C space. And when you look back in the original workspace, we can see that although the robot gets close to the original obstacles, because it will never touch the obstacles because the shape of the robot has been accounted for in the C shape. So this gives us a proposed pipeline of how we should approach these type of problems. The first is to collect data about the obstacles and the robot. The next is to approximate the shapes using polynomial sublevel sets. And that's through approximating this indicator function with the polynomial. Next is to take the Minkowski sum between the polynomial sublevel sets. And that also involves approximating another function from below using a polynomial. Once you have these polynomial sublevel sets, you can enforce them as constraints in any path planning algorithm you choose. And there's a lot of path planning algorithms. So for future work, I would still like to improve the surface reconstruction methods. I would like to make the method more robust to noise in the point cloud data set or sparsity. I would like to improve the clustering approach. In the clustering numerical example I showed, I just used k-means, but there's other clustering methods that could be better. I'm still not satisfied by approximating these shapes by 20-degree polynomials. I would like to get a complicated shape with a lower degree polynomial. So I'm looking at ways to improve that aspect. For the Minkowski sum approximation, I would like to improve the speed of the approximation for more real-time implementation, and also to bound the error in the approximation. At the moment, the theory just says as the degree tends to infinity, our approximation error tends to 0. But if you're interested in a particular approximation error, I can't tell you what degree you would need to select, just a sufficiently large degree. And I'd also like to account for moving obstacles, because at the moment, all of the obstacles were static. So that's the end of my talk. Hopefully I didn't overrun.
No,
Thanks.
we have still 2 minutes. Thanks a lot, Morgan, for this really nice talk. We do have one question in the chat. So thanks for the presentation from Mohammed Boukev. Quick question, maybe I didn't pay attention, but why do you want the obstacle region to be larger? Aren't we restricting the possible trajectories for the robot? I understand that it is safer, but aren't we losing some freedom?
Yeah. So the issue is that most of the path planning algorithms consider the robot as having no shape. So it's just a infinitesimal point. And if it does have a shape, then even though this infinitesimal point might get close to an obstacle, this would still cause a collision because you've neglected the shape of the obstacles. So to be able to use these algorithms, you need to transform the problem into C space and enlarge the obstacles. And these are then you can then consider the object as an infinitesimal point and run any algorithm you want.
Okay, thanks, Morgan. Nikos, we have, yeah, the floor is yours, Nikos. You can ask your question.
Yeah, thank you. Thanks for the presentation. I will read the paper. It's very interesting. I have a quick question. I'm wondering if you have results on approximating, as you said, intersections or unions of basic semi-algebraic sets with a single basic semi-algebraic set, like a polynomial inequality, and then if there is any comparison, maybe if there are theoretical, let's say, considerations like negative results on the bounds of this approximation.
Yeah. So I've got results on approximating these intersections and unions, but I don't have a bound on the approximation error. I just have a result that says as the degree goes to infinity, you get a bit better and better approximation. The approximation error goes to 0 in the volume metric, and in some cases in the Hausdorff metric, depending on how you set up the optimization problem. But I don't have a bound. So if you give me a particular degree, I cannot tell you the error before I run the optimization problem.
Oh, thanks. But would you know of any theoretical bounds, or do you know if there exist any theoretical bounds on the approximation accuracy?
There are alternative algorithms, and they might give you a bound, but they don't show that they don't show that they converge. So as something goes to infinity, the error goes to 0, but they can potentially give you a bound.
Okay.
So you could have a look at the literature review of the paper for the alternative methods as well.
Yeah, thanks a lot. Thank you.
Nice.
Thank you both, Nikos, and thanks, Morgan, again. So we will move to the third talk and the last of the first session. It will be given by Dr. Thomas George Thuruthel from the University College London. He will be talking about learning full body deformation of soft robots using end-to-end models. Maybe, Thomas, if you can share your screen while I will be briefly introducing you. So Dr. Thomas is an assistant professor in the Department of Computer Science at UCL, and his research interest is on control of soft robots, design optimization of soft body system, development of novel soft sensors, and dexterous manipulation using visiotactile information. The floor is yours, Thomas. Thank you for being with us today.
Great. Thank you, Zehor. Can you hear me?
Yeah, we can.
And you can see my screen as well?
Yeah.
Perfect. Great. Thank you for the invitation. Like as I said, I'm Thomas George Thuruthel, lecturer at UCL. And today I'll be talking about how we can learn full body models of soft robots using end-to-end models. So just before I start, I just want to quickly introduce the kind of robots that I'm interested in. Largely come under this set called soft robotics, where we're trying to make robots with soft materials. There is a lot of diverse designs you can use that come under this field of soft robotics. It's quite interesting to control engineers because they pose a significant challenge in modeling and control. I will quickly go through some of the state-of-the-art techniques when it comes to modeling. Broadly speaking, if you look at analytical modeling in software, that is mathematical models, they come under the spectrum where you have really simple low-dimensional models like constant curvature models, which are very good for control, but tend not to be very accurate, especially when you have complex shapes and various designs. And on the other spectrum, we have finite element models, which work very well in terms of capturing the action dynamics and the properties of the system, but they're not very useful for control problems because of their computational difficulty. So I have been working during my PhD and as a postdoc on this idea of using machine learning methods for the same problem of controlling soft robots. And before I show the methods, this is what the state of the art in that domain looks like. So learning-based methods, in short, works very well if you want to do like control of the end effect of kind of simple systems. So you can, using pure learning-based techniques, have accurate models so that you can control your tip in some known trajectories, in a predefined trajectory, or make it reach certain locations. So that's well and good. And if you were to look inside these models, essentially the fundamental building block is a machine learning model, typically a simple neural network which approximates how the underlying physics looks like, but in a low dimensional space. So you have this model which takes in the inputs that drive the system, so the control inputs, and predicts how the control variable would behave. So, and in most cases, that looks like the end effector moves. So if you were to come back and look at how this looks in the spectrum of our analytical models, so these still belong under this low dimensional space. So these models still predict how the system would behave, but will only give you information about something like the end effector position. So there is not yet a way so that we can learn how, for example, the whole shape of the system will evolve. And there are no good techniques to parameterize these kind of learning-based models. So in this talk, I'm going to present you some ways of doing it, and specifically we're looking at end-to-end learn models for software books. What do I mean by end-to-end models is we have, again, some machine learning model which, based on the actions that you are taking, instead of predicting or estimating these control variables, we're going to just purely predict what would be the raw sensory data. So if we're looking at models, for models, that's how it looks like. And if it's controllers, then we, based on the raw sensory data and your target, these controllers should give you actions, the best actions you should take. Specifically, we're going to now, in this talk, look purely at visual sensors. So assuming that you have a camera looking at the system, what we want is models that will predict what this camera should see, or if it's controllers looking at purely the raw camera input, can we take the best actions so that we can reach our targets? It's not a new idea. So there is a lot of work on this idea, a similar principle of developing word models from raw RGB images. A lot of it is in simulation, and they have not been used in software. So that's what I'll give you a few examples of how that looks in this domain, and some of the future works. We'll start with how we can learn end-to-end controllers for static cases. So setting the stage up. So what I mean by statics is assuming that the system, if I give it a constant input, would reach a quasi-static configuration. This allows us to formulate that there's a function which maps from this constant inputs to a static configuration. The objective of the static controller is then to invert this. So if I wanted to reach a static configuration, can I give control inputs that will eventually ensure that my system would reach this configuration? And in our end-to-end framework, what we essentially want is then, if I give an image of my software robot of the configuration that this robot should reach, can I then give control inputs, static control inputs that would take me there? The same problems that we have even in rigid robots apply here. So the inverse of this problem is not well defined, but the way around it is the same solution that we use even in rigid robotics. So what we do is we invert this problem locally, which is a functional mapping. So what we say is, given our current configuration, visual configuration, what our controller is trying to do is instead of taking one-shot solutions, it's going to give us actions which take us closer and closer to our desired target. So this is essentially our local inverse kinematics formulated in using this visual space. How does that look like? So what we do essentially is create this data set for learning, where we take small steps, learn this mapping from current image to the next image. What is a small action that I can take that will take me to that next visual space? Collect a lot of data sets like these and learn this mapping using simple convolutional neural network. Once you learn this mapping, then you can develop controllers which take incremental actions to reach our target. So here we are showing some results of how that looks like. You can see that on the left-hand side of each pair of images, we have the target image that we want to reach. These are static targets. And these are the actions that the robot takes. So this robot, specific robot, is controlled by 6 pneumatic chambers. So you apply pressurized air through chambers, which makes it deform. And you can see the controller working. It's able to reach these targets reasonably well, even though there are like visual noises because of lighting changes. And it doesn't reach it in one step, it takes incremental action. So it has this feedback loop, which also makes it a bit more robust to uncertainties in the model, which is quite common in these kind of systems. The remarkable thing is this can also be generalized. So now what we see here is a target which is drawn by hand. So using using Microsoft Paint, we just drew the shape that the robot needs to reach. And although some of these shapes are not reachable, not physically possible, we still do see the system trying to reach the best possible configuration given its constraint, which is again remarkable, given that it's not learned on this data set. So that's well and good. But even then, we still have this assumption that this robot has to move slowly so that the quasi-static assumptions are valid. So in order to be more generalizable, we need to then figure out ways to learn end-to-end fully dynamic models. So in this case, now we're not going to learn the controller. First, we're going to learn the full dynamics of the system. And so how that looks like in our scenario is we have a machine learning model which, given the action, predicts how the camera expects the robot to behave in an iterative way. So it takes back also the feedback of your previous predictions to take to predict the next actions or the next expected visual data. So in order to do this, we also need to modify the learning architecture a bit so that it can incorporate dynamics. So what we see here is an LSTM combined with a convolutional neural network. The LSTM would capture the dynamics part of our model, and the CNN then upscales this to this visual domain. Once we have this learn fully forward dynamics, then you can use traditional optimization-based tools for developing your control actions. In this case, we're going to learn a purely open loop for control policy. Key thing to note here is now our targets are going to be like given in the visual domain as well. So we need to do this, formulate this errors or the objectives in the visual domain as well. So here what we are doing is very simple thresholding for our targets, subtracting what we see versus what we expect, and then trying to reduce this mismatch between two images. And we'll kind of show you some results on how that looks like. So again, like before, we have a desired shape given as visual images. And in the center, what you see is what the learned model predicts. So this is a purely learned architecture which predicts how the actions affect this visual domain. That's why it's blurry. And on the right-hand side, you see what the real robot would behave like if I had given those action inputs to the real system. As you can see, it does reasonably well, even though the model is not that accurate, especially at the tip. There are good reasons for that. But now that it's a fully dynamic simulation, you can also control the trajectory of the robot in real time, which is really cool. And as before, we can also now play around with how we specify targets. So we can add virtual targets as before. So in the first example, what we do is we add virtual obstacles in the visual domain, and then make the robot follow trajectory without touching this virtual obstacle. Again, works reasonably well. It is again not very good at predicting the tip position, which means that there would be errors in that region particularly. But this is something that definitely can be improved. We can also play around with how we give targets. So this is a target which is completely abstract. But since we are purely looking at matching the image as closely as possible, the controller works really well. And what's also remarkable is that the amount of training data that we require for this kind of learning is significantly lower than you would expect. So this fully dynamic model was learned with just few hours of data that is collected, which means that there's a significant scope for improvement in accuracy if we collect more data with over diverse conditions as well. And the fact that you can play around with the targets gives us a lot of freedom. So not only can we do shape tracking, but it's also feasible that we can do end effective tracking as well by adding a state estimation pipeline in our learned visual model. So these are the two main works that I wanted to present. I will quickly show some of the things that we are working on right now that we're interested in. So this is a slightly more complex challenge and that involves contact.
So 5 minutes. Just
Oh, perfect. So I'm going to finish well before that. So the tricky bit with soft robots is that when you have when you do not have contacts involved, the dynamics is quite well behaved. It's pretty low dimension that you can learn with a few data sets. However, when we have contact with the environment, especially if the environment is unstructured and unknown, then the state space blows up, and it's essentially impossible to predict what is the dimensionality of what is the minimum dimensionality that you require to fully represent your structure. Whereas if there's no contact, you can more or less put a bound on it based on the number of actuators that you have. So this problem, when it comes to learning, is again challenging because now you also need some information about how your environment looks like to have a model which predicts your future states. So we've been looking at how we can do that. So of course, we need some information about the environment. So what we can do for providing that information is give it these models an initial image of how the settings look like. So what we mean by that is we have a soft robot which is interacting with the environment. We give it an initial snapshot of how the environment looks like, and then from then on, we want a model that can predict how the interactions would look like. So this is some of the work, some results from work recently done. It is still a work in progress, but at least it sets up the stage for what we're interested in and some of the things that we are looking forward to do in the next few years. So this is a setup where you have a soft robot. We also do some simulation studies to see how the learned model behaves with different settings. So this is a results from the simulation study showing that with simplistic obstacles in the way, we can fairly get good results on how the software will deform. Keep in mind, it's very difficult to generalize to different obstacles. So we have to ensure that we get a fairly good subset of data of obstacles in our data set. At the moment, we are limited to very simple shapes. So this is a data collection protocol. So where we have soft robot interacting with obstacles of different shapes. We record the deformations and use a simple, again, convolution neural network to predict the deformations. Long story short, they're not very good in a lot of circumstances, and there are very good reasons for that, because in essence, This problem is highly stochastic. It's very difficult to predict how the system would behave purely given the action and the initial settings. And in order to solve this issue, the only way forward is to have some primitive information about context. And this could come from either tactile sensors or other form of sensory feedback. You probably cannot do a fully open loop predictions to get accurate visual information about how the system will behave. So that is some of the things that we are looking for, studying, investigating these days on how we can add also contact information using soft tactile sensors to then create these world models, visual world models. Yeah, thank you so much for your time and attention. I believe I have some time to take some questions.
Thanks a lot, Thomas, for the presentation. I think really insightful to see how we use learning to predict models. We do have 2 minutes for questions. There is one in the chat. I don't know if you want me to read it for you.
No, I think I can read.
Okay. I can read it for maybe. How computationally efficient are the models for training and for real-time inference? That's the first bit of it. I think we have a couple of questions in one. And how do you take into account the constraints of actuator? Are you hard constraining the models? Do you consider the optimality of the generated actions or trajectory?
Perfect. Good question. So I assume that you're talking about the second work where we're doing this fully, learning the full dynamics of the model and then doing the controller. How computationally efficient? So they're not bad. So they are, so we're running it on desktop computers. So we're not using high performance computing for these models. I believe we're not using GPU, we're just simply using GPU for our predictions. And they can work in real time. So the forward models would be able to do faster than real time simulations. However, when we have the optimization in the loop, that does not work in real time. So this problem of getting your right control actions, that optimization loop does take time because it's essentially we have to do numerical optimization in a very high dimensional space. So that does take a bit time. So that's why we are doing an open loop control. So the models themselves are quite real time. And maybe we can linearize them to make our optimization real time as well. And because we are doing like traditional model predictive controller, all the constraints can be taken into consideration. So we can put hard constraints on actuation limits. If you want, we can also put optimality conditions on the energy that you're spending, which is all doable because of this framework. So which is again quite cool. Only the model or the forward dynamics model is learned. Everything else is traditional control techniques.
Thanks a lot, Thomas. If you have any other question for Thomas, we will again have this open discussion to build more discussion with the speakers at the end. So yeah, feel free to ask Thomas about any question you might have. So as we are running a bit late, given the start, the late start, we will take shorter break to grab a coffee and or water. So we will be resuming in 3 minutes, 11:45, for the second session. So see you in 2 minutes.
Hi, Zehor, Hector here. Can you still hear me?
Yeah, Hector.
I just a thought. The time goes quite quickly, doesn't it? And my movie is quite long. I wondered whether we could start it after the word, not wait for the words kinetic to come up and just. I presume you could speed it up a bit if I need to. Is that correct? Just move it along.
Yeah, I think the second section are only like 5 minutes talks. It's not 20 minutes.
Okay.
So hopefully, like, yeah, we will not overrun the 5 minutes.
Okay. Okay.
Yeah,
Cool.
so I'm like, yeah, and then we have one speaker less, so it should be
It
hopefully
should be fine. Okay, good.
resuming to the standard time, Hector.
All right, good. Thank you.
I think we can make start with the second session. So the second session will be rapid fire talks to get the opportunity to know the research from different like researchers and colleagues in the field. So we're gonna start the first talk of the session that will be given by Dr. Junyan Hu from Durham University. So he will be talking about cooperative control in swarm robotic. So Junhan, like his work is in swarm intelligence, multi-agent system, cooperative path planning, and adaptive control with application to autonomous vehicle and intelligent robotics. Junyan, the floor is yours. Can you hear me?
Yes, yes. Thank you so much for the introduction.
So yeah, for those talks, again, they are 5-minute talks, 3 minutes talk, and then 2 minutes questions. The floor is yours.
Okay, thank you. Okay, thank you for the introduction. My name is Junyan. I'm currently an assistant professor in the Department of Computer Science at Durham University. So my research interest is mainly about cooperative learning and control in swarm robotics. Okay. So for some of you may not very familiar with the research domain in swarm robotics. So here I may just have a brief introduction. Actually, the area of swarm robotics is mainly motivated by some collective movements in nature. For example, the bird flock, the fish school, the bee colony, and the sheep flock. So computer scientists, control engineers, and even biologists, they are trying to learn those collective intelligence from the animals such that we may give such intelligence to the robots. And then the robots could also play a very important role in our daily life and real-world applications. Regarding the general framework, we may mainly rely on the centralized system or the distributed system. While the centralized system may be very traditional, and it may also suffer from one point of failure of the system. So in recent years, we are more interested in the distributed system, such that the robot could share information with their neighbors, such that in the end, they could accomplish complex tasks collectively. So in order to generate or develop the intelligent cooperative robots, we may mainly rely on some techniques from different domains like artificial intelligence, control, and robotics. In our research group, the artificial intelligence are mainly used for high-level decision-making and planning. So we may rely on machine learning or deep learning techniques. And then we also need to use control theory to deal with low-level dynamics and motion control. And in the end, we also need some hardware just to show the effectiveness of the proposed learning and control techniques. So due to the time limit, I won't go into the technical details. Instead, I would like to show some of our previous simulation results or the hardware experiment results. If you have more interest about the technical details behind these videos, please feel free to check our recent publications. So in these examples, we have already applied some cooperative learning and control algorithm to autonomous vehicles or mobile robot swarms. In these slides, we also try to develop different applications by using a swarm of the ground mobile robots, as can be seen in these videos. So when properly designed, a swarm of these mobile robots could cooperate with each other. And recently, we have also set up the drones experimental setup in our department at the Durham University. And our focus is slight shift to the area swarm robotics, such that we are more interested in how to develop a more efficient and time optimal trajectory planning for a swarm of the drones. So here you can see that of some of our recent experimental results. For future works, we are very interested in develop novel robotic networks and also to combine the bio-inspired swarm intelligence algorithm with the distributed learning methods such that those robots or vehicles or drones could be more intelligent. And as one of the applications of the swarm robotics, we are also very interested in connected vehicles. So thank you so much for listening. Please let me know if you have any questions or contact me via email. Thank you.
Thanks a lot, Junyan. Like while the second speaker, Leonardo, will share his screen, we do have time for one quick question for Junyan. And any questions? If not, yeah, maybe like I think we will have more like an open discussion at the end for those second sessions. So thanks a lot, Junyan, for sharing your work. See you in a bit. Leonardo, Dr. Leonardo Stella is our next speaker from the University of Birmingham. He will be talking about learning Nash Equilibria via innovative dynamics. So Dr. Leonardo, his research interests are in game theory, control reinforcement learning, and multi-agent system. Leonardo, the floor is yours.
Yeah, thank you very much. Thank you for inviting me to this workshop. So I will jump directly into the problem due to the very short time. So multi-agent reinforcement learning has achieved incredible results in the past few years, and there's been a huge interest in the control community to apply reinforcement learning and multi-agent reinforcement learning to multiple problems. Consider, for example, energy systems, consider sensing design, multi-robot systems, and so on and so forth. However, there are still a lot of open problems. I will not provide details on these open problems. Specifically, the one that we will focus on will be instability, but I will give you an example to understand the issue here. So if you consider a very simple rock, paper, scissors game, typically these algorithms fail to reach the optimal policy, which is the mixed strategy Nash equilibrium, basically playing rock, paper, and scissors with 1/3 of probability. And this is due to the nature of the game, which is a cyclic symmetric game. And we will see why zero sum is important in a second. So research, or a very important line of research, has looked at learning Nash equilibria to ensure that these algorithms have theoretical guarantees that they can learn this optimal solution and thus break the instability issue, and also to account for scenarios where maybe the payoffs are only partially known. To do this, one important set of tools is provided by evolutionary game theory. And you can see here one of the most common models, which is replicator dynamics. In other talks today, we have seen that control is now using more data-driven approaches. What we are suggesting here is to use tools from control or from the study of evolution game theory and the models in evolution game theory to ensure some desired properties of the algorithms. And in particular, what you see here, the replicator dynamics, can be expressed as the proportion of a subset of a population of agents that chooses one particular strategy. In this case, it's X1. And this evolves as how many of these agents are choosing that strategy times the difference between how good the strategy is, which is expressed by the element in blue, the fitness of the strategy, versus the average fitness of the population. Now, what you see here is, again, rock, paper, scissors, but the issue is that replicator dynamics do not directly converge to Nash equilibria in zero-sum games. So you see on the left-hand side the trajectories around that stable center, which is the Nash equilibrium. And on this picture here, picture C, I hope you can see my mouse, through a time average, so through a slightly different process, This picture is taken from a paper called the Neuroreplicator Dynamics, a very important paper by the Google Group research. They are able to retrieve the Nash equilibrium, and so the trajectory converge. However, when it comes to learning due to sampling issues, you can see here a softmax policy gradient algorithm that fails to achieve the exact Nash equilibrium when we take the time average. So what we propose is to bypass the issue of time averaging replicator dynamics and instead develop a new family of algorithms that is based on innovative dynamics. This is due to the property that in null stable games, of which zero-sum games are a big important family, directly converge. And to do so, we change the sampling process in a way that resembles experience replay, which is a terminology typical in reinforcement learning, which means basically imagine a batch of samples that moves along the learning trajectory of your algorithm. And we call this experience replay innovative dynamics. Now, let me show you the results, and then I will conclude my talk. So first of all, we ensure convergence guarantees of our algorithm as it is in other state-of-the-art algorithms, for example, cross-learning, for example, neuroreplicator dynamics. This is shown in this picture. So on the left-hand side, we have the original dynamics, and the right-hand side, we have the learning trajectory of the algorithm, which is able to find the Nash equilibrium. And finally, our algorithm outperforms, or our family of algorithms outperforms other algorithms in the field, are the state-of-the-art algorithms when it comes to non-stationary environments, which means environments that have changes over time. As you can see here, the changes are indicated in red, and this metric here, Nash-Conv, is basically a way to evaluate how close we are to the Nash equilibrium. As you can see, our two algorithms here, BNN and Smith, stay very close to the Nash equilibrium with respect to the changes on the environment, whereas cross-learning instead deviates quite a lot. So I would like to acknowledge the amazing work done by my PhD student, Tuo, and the collaboration with Julian before saying thank you for inviting me again. Thank you very much.
Thanks a lot, Leonardo, for the talk. I think we can take the question maybe at the end in the open session so that we can move with the other talks. Thanks again. So our next speaker for this session will be Dr. Thiago Burghi from the University of Cambridge. So yeah, Thiago, if you can try to share your screen. He will be talking about estimation and control of living neural circuits. So Dr. Thiago Burghi, he is a research associate in the control group at the Department of Engineering in the University of Cambridge. His research is at the interface between nonlinear control theory, system identification, and artificial and biological neural systems. The floor is yours, Thiago. You have 5 minutes.
Yeah, thank you. Thank you. I'll try to do it in 4. We'll see. So I'll just jump straight into it. So the motivation for my work starts with the fact that qualitative changes in brain dynamics affect human behavior. So as you can see here, an epileptic seizure is caused by the sudden synchronization of cortical brainwaves. And also the fact that modern new technology allows us to interact with those brain dynamics in real time. So the natural question which arises is whether we can restore normal brain function using feedback control. So naively, the picture would look something like this. You use the usual things that we are used to. You do system ID on the brain dynamics, and you design a control law to solve it. The problem, however, you immediately run into big challenges because neural systems, they're unlike traditional engineering systems like mechanical and electrical engineering systems. They're biological, which means they have huge uncertainty. They're plastic, which means that they adapt to you in real time. And they're excitable, meaning the signals are composed of spikes and bursts. So there's a lack of suitable tools to address this kind of problem. In my research, I adopt a very bottom-up perspective. And we've been implementing closed-loop control of individual neurons, so a few at a time. And we're able to do this because, as it turns out, there's this experiment in electrophysiology called dynamic clamp, where you're able to measure the membrane voltage from individual neurons and use a computational model to decide what's going to be this applied or control current they inject back into the neuron. So one of the difficulties we face here is the fact that even at the level of small neurons, there's huge uncertainty. As you can see, there's a picture of a real neuron. It looks very complicated, and it is. So that if you try to use first principles models that you can find in the literature to design your control algorithm, you're not going to be very successful. So one of the things I've done in collaboration with Tim O'Leary and Yves Marder, we designed these so-called recurrent mechanistic models, where we respect the physics from neurodynamics. However, we change some parts of these traditional models and use LTI systems in conjunction with artificial neural networks to make the model better at capturing that uncertainty. So using this type of modeling methodology, we've been able to design adaptive control laws for small neural circuits, again, a few neurons at a time. For instance, here, this is a neural circuit. You measure the voltage from 2 of these neurons, and you see that the neuron PD there is inhibiting neuron LP. So every time PD bursts, LP stops firing, right? Now, if you try and use our methodology and use dynamic clamp, you can estimate models for these neurons, and then you can, for instance, reject that synaptic current, meaning that now PD is not inhibiting LP anymore because the signal has been rejected in real time. So of course, we don't want to stay, we want to scale this up to large networks. And the problem there is the fact that it's usually very hard to measure the voltage from more than a few neurons at a time very reliably, which means that networks will have many unmeasured states, voltages, and will have hidden neurons. So what you do with this problem here is that supervised learning techniques or system ID techniques immediately result in vanishing and exploding gradients in the optimization problem due to the nonlinearity of the neurons. So one of the approaches we've been looking at is the design of so-called Hebbian observers. And the idea here would be that each of the hidden neuron in a network would try and learn its parameters more or less like an adaptive observer, meaning each individual neuron is constantly trying to estimate both the states and the parameters of its presynaptic neurons. We have some results related to that, at least for a few neurons at a time, and future work will address the problem of adding more neurons to the picture. And interestingly, we can connect this kind of approach to what people have been doing in computational neuroscience, where they design so-called biologically plausible learning rules, which are unsupervised and local, to try and mimic the way that the brain actually learns. So thank you. I think that was all.
Thanks a lot, Thiago. Like, maybe so if you have questions for Thiago, so we have 1 minute for one quick question, while our next speaker will be setting or share the screen, Dr. Francesca Boem. So Thiago, one quick question for you. Like, what do you think, like how your approaches, control and observer approaches will scale if you take a multi-neuron, which we know it's a little bit complicated.
Yeah, so the idea is that if you look at a neural network, the structure of the model, it has more or less the same structure as the model of a single neuron, because you can think of a big neural network and you can think of the synapses between the neurons inside that big neural network. You can think of those synapses as if they were internal currents of a single neuron. So the same strategy that you could potentially approach to a single neuron, you could try to just mimic that at the network level just because of the structure of the system. So you end up with like internal dynamics, which have the same types of properties in a sense. So that would be the strategy. But yeah, this is work in progress. So, more on that later.
Yeah, thanks a lot, Thiago. So our next speaker is Dr. Francesca Boem from the University College London, UCL. She will be talking about online end-to-end learning-based predictive control for microgrid energy management. So Dr. Boem is currently an associate professor with the Department of Electronic and Electrical Engineering at UCL. Her research interests include distributed fault diagnosis and fault-tolerant control methods for large-scale network system, safety and security of cyber-physical systems, learning-based control. The floor is yours, Francesca.
Thank you for the introduction and thank you for inviting me. So I will start again very quickly. With a motivating example. As you may know, microgrids are small-scale grids, including loads, generation, and storage units. And the goal of the energy management system is to optimize energy production and storage in order to provide the power to loads and minimize costs. However, there are some challenges, and the main comes from uncertainty that we have in the production generation from renewable sources, the electricity price, but also the uncertain load demand. A standard approach that can be found in the literature is to first design offline a predictor for the uncertain profiles and then apply it online using the forecasts to compute the scheduling. For example, using a model predictive control. However, this does not take into account of potential changes in the environment, for example, such as the installation of new loads, new equipment, or faults, or shocks in the market, in the electricity market. And does not take into account on the uncertainty in the dynamic model that the MPC considers, in this case, the storage, so batteries losses, aging, and faults. What we propose to overcome these limitations is a novel learning-based predictive control architecture, where we embed the MPC optimization problem as we embed it as the last layer of a neural network as a differentiable optimization layer. And this allows to directly train our neural network in an end-to-end fashion, so using a task-based loss, directly targeting the control performance instead of the mean square error of the uncertain profiles. In this way, we can continue to guarantee constraint satisfaction thanks to the use of the MPC problem, but we allow the model to learn uncertainty in the dynamic model too. Moreover, in order to allow this real-time implementation and to take into account of time-varying uncertainty, we designed a novel online training algorithm that allows to take new data into account and to update the weights of the neural network as this data comes available, and this permits to adapt the neural network model to the changes of the environment. We have done experimental results with real-world data where we confirm the superiority of the online learning compared to neural networks that do not adapt their weights anymore. And we have seen how our algorithm allows to predict more carefully, more accurately, changes in prices, for example, or changes in loads, and how this allows to adapt to time-varying profiles. Moreover, and very interesting, we have seen that the task-based approach allows to achieve better control performance even when we have higher mean square error in the prediction, and it manages to take into account of the uncertainty of the battery model, somehow correcting the not correct parameters that we might put in the MPC. In this way, it allows a robustness to unknown model parameters. Finally, we have seen very good transfer learning capabilities, and not only we can move from one model to another, so different microgrids in this case, but also we have seen that pre-training in online learning fashion, our method on a different microgrid allows to obtain better generalization and better performance in a completely different system. So I will conclude just showing some list of references where you can find everything that I'm not able to tell you now. The simulation code is available online. I would like to thank my PhD student, Vittorio Casagrande. And yeah,
Thanks a lot, Francesca. We
again.
have one quick question, like if you have one quick question for Francesca, while again, our next speaker, Dr. Jack Umenberger from the University of Oxford will share his screen. Any questions for Francesca? So, like, if not, like, I have a couple of like, we do have one quick one. Do you have any certificates or guarantees, Francesca, for the learning-based controller? So we
Well,
have.
there is not a certificate, but by embedding the MPC directly, we allow the constraint satisfaction implicitly. So it's somehow embedded in the architecture, how we design it. We can force some constraints, which could be operational or safety constraints.
Okay, lovely. Thanks a lot, Francesca. Okay, our next speaker is Dr. Jack Umenberger from the University of Oxford. He will be talking about optimization for real-time grid operation. So Dr. Jack is a senior research fellow with the Department of Engineering Science and Zero Institute for Zero Carbon Energy Research at the University of Oxford. So his research interests include optimization for control and decision-making with a particular focus on data-driven or machine learning augmented approaches and application to energy system. Jack, the floor is yours. You have 5 minutes.
Thanks very much for the introduction and the invitation. Can you see my slide and screen okay?
Yeah, we can.
Okay, great. Yeah, so this work is really about solving control problems that blend both continuous decision variables and considerations with discrete decision variables. So the motivation really came when I was a postdoc in Russ Tedrake's robotics lab at MIT. And this video here comes from the old DARPA robotics challenge days, but it's quite clear that in this kind of robotics problem, you have continuous decision variables around joint angles and force and torque, but also these kind of discrete decisions you have to make, right? Which stone should you step on, or should you go left or right around the obstacle? At the time, I was in Russ's lab. We were mostly working more on robotic manipulation, but you get the same kind of considerations. Obviously, very similar continuous decision variables, but the discrete or combinatorial aspect of the problem is more about kind of collision avoidance. Do you go over or under some arm, or do you go left or right around some obstacle? These days, I'm also quite interested in problems in the electricity grid, especially real-time balancing of energy. So here, the system operator puts in a request for some more energy. There's explanation from ESO's slides here. And then you have to decide how to meet that requirement for energy in the most economically efficient way possible. So the continuous variables here are obviously, the power and the ramp rates of the different units that you have. But then there's a number of interesting discrete and combinatorial considerations. So most obviously, should you turn on or off a unit at all? If you turn it on, you may have to leave it on for a certain amount of time. And there's also constraints on when you're allowed to ramp up and ramp down. If you've been ramping up, you can't ramp down straight away. You have to have a kind of flat top. So this is really the summary of the talk here. So for tackling these control problems that blend both discrete and continuous components, we propose this graph of convex sets family of problems. So you can see that the motivation comes from the classic shortest path problem, which is purely discrete. But in the graph of convex sets problem, instead of just moving from one vertex to another, you're allowed to move from any point within a convex set to any other point within another convex set. And instead of paying a fixed edge cost for making that transition, you pay a cost that's given by a convex function of the two continuous variables. So this kind of problem formulation gracefully blends both the discrete decisions, which are encoded with the graph, and also the continuous decisions, which are encoded with the convex sets and the edge costs. So I guess that the main contributions, I suppose, are proposing graph of convex sets as a modeling framework. I mean, I don't really like this word framework. It just sounds like, you didn't really figure out the details, but I think it is a nice modeling framework and a nice modeling language. The second kind of real contribution, I guess, is a good mixed integer convex formulation of this problem. So by good, I mean that you get a good trade-off between size and strength of the mixed integer formulation. So you can actually solve it efficiently with branch and bound in many cases. Okay, so in the interest of time, maybe I will skip over this example and you can ask me about it later on in the questions if you want. But I'll just close with this. So here's an example on that electricity grid balancing problem. So the shaded region is the requirement for more energy over 20 minutes that the system operator picks. This is a simplified example with one generator. This is the optimal path that you can take for this particular unit. You'll notice that the ramping constraints are power dependent, and the kind of standard big M formulation of the problem just completely ignores these constraints in the relaxation. We're just looking at the relaxation here, ramps up and down way too quickly. But the graph of convex set formulation, even though it's not perfect, it's still is much closer to the optimal solution. So I will close there.
Thanks a lot, Jack, for the presentation. We do have 1 minute for a quick question again, while our last speaker, Nicholas, if you can share your screen. Any questions for Jack? No? Yeah, if you do have like again, we will have an open discussion, which is free discussion. I will be asking our speakers a couple of more questions. So do prepare your question for our speakers from the second session. Thanks a lot, Jack, for being with us today. Our last speaker for the second session is Dr. Nikolaos Athanasopoulos. I'm sorry, Nikos.
No, that's perfect. Thanks.
He is from the Queen's University Belfast. He will be talking about computational-aware set-based analysis and control. So Nikos, he is a senior lecturer in control in the School of Electronics, Electrical Engineering and Computer Science at Queen's University Belfast. His research interests are in control theory and engineering with a focus on hybrid system and set-based methods for cyber-physical system. Nikos, the floor is yours. You have 5 minutes.
Yes, thank you, Zehor, very much for organizing, and thank you for the invitation. I just would like to talk about what my interests and some of the people in our group's interests are, and to share.
Can you put it on full screen, Nikos, please?
Is it not shared?
It is shared, but not full screen. Presentation mode. I think on the bottom on the right, we can see like.
No, I'm sharing already, but I have maybe too many.
Can you hear us, Nikos? I think we lost Nikos. So we lost Nikos. So let's see. Oh yeah, he's back. Okay, Nikos, thanks.
Yeah.
You can see it now.
Is it okay?
Yeah, it is. Thank you.
Okay. Thanks. Thanks again. So just like a very quick introduction to what we are doing here, and this is like just a motivating slide. So we're mostly interested in computing invariant sets and doing research on scalable set-based methods. And the basic principle is that we are looking to find invariant sets or characterize the properties of the state space with the state subsets of the state space with some properties. So the property we're looking for in this cartoon is an invariant set, basically confining the trajectories of a dynamical system in a subset of the state space. And in this sense, if we have this confinement, that means that wherever we have some constraints present, by confining the system's trajectories in a subset of the state space, then we can have constraint satisfaction. So we can start generating certificates of safety, but also if we twist the problem in a specific way, we can have performance certificates and so on. And this is important for many problems in engineering related to planning, but also scheduling, and in general, where we have cyber-physical systems and systems with constraints. Now, I'm happy that many speakers talked about these problems and challenges. So there are many people that have been, and groups and methods that have been working on these problems. And there are methods in this more conventional linear and convex setting, methods for computing invariant sets for hybrid systems and for the general nonlinear case. But what I would like to focus on or like to highlight are the challenges of computing these sets, especially if we're dealing with challenging systems or challenging environments, for example, high-dimensional systems or nonlinear dynamics or time-varying dynamics as well. So yeah, these sets can become extremely complicated and complicated also to characterize. So one of the ideas that we had is to cheat a little bit. Instead of computing invariant sets, starting from simple ones and then incrementally changing their shapes. So this is one pictorial of how to do this. And then what we tried to do is to mitigate this complexity in computations, but looking at the combinatorial structure of these invariant sets, in this specific case of polytopic sets, and looking at their phase lattice. And that it's not only for this two-dimensional case, but we can expand it to any dimensions, and we can have an a priori, let's say, estimation of the complexity of the resulting sets. And now I'm just gonna finish with a couple of applications. So we have applied some of these set-based approaches that we've been using to applications in robotics, where we're trying to solve first the trajectory planning problem by projecting the dynamics of here in this case, an end-linked robotic manipulator into two dimensions in the pseudo distance and pseudo velocity of the around the path. And then the next step that we try to do is to do a path planning by following the celebrated methods using motion primitives in robotics. But this time we're trying to match like cut and glue trajectories using these ridge avoid sets that we have pre-computed. Another application is using invariant sets to calculate and to quantify the impact of attacks on cyber-physical systems, but I will not go into more details. And the last, the more classical application would be on looking at path planning and motion planning for, in this case, for high-speed marine vehicles, using, again, reachability and set-based methods. Yep, so some related publications, and thank you very much.
Thank you very much, Nikos. We do have 1 minute for Nikos for a quick question before we move to the last and third session. So, any questions for Nikos? If not, so what I will take 5 minutes break instead of 10 minutes. I think we are on time now because one of the speakers couldn't make it, but so we will be launching the last session, Industry Meets, AI and Control and Panel Discussion. I'm very glad that we have a session with an industrial-like person to talk about the challenges that face AI and data in industry, and talk a lot more about his experience working in the industry. So we will start the last session at 12:15 in 4 minutes. And while I will be setting like the presentation. So Hector, we will be starting in 4 minutes with your talk.
Yeah, that's fine. Thank you.
Okay, I think we are ready to start with our last session on data, AI, and control meet industry. I'm very pleased to have with us today Hector Figueiredo, who is a charter engineer and capability lead at QinetiQ, specializing in autonomous system. So Hector, he is leading research teams in diverse autonomy-related technologies being developed both in-house and externally, which includes application of system engineering principle to underpin research, development, and exploration. Today he will be talking about the intersection again between data, AI control, and the industry, and share his expertise. Hector, the floor is yours.
Thank you very much. Apologies at the outset because I'm just recovering from a cold. It says industry view. I think it's fair to say it's one industry view, and in particular, I've tried to structure my presentation around the topic of maintaining effective human-machine partnerships. And more than that, I think the other thing to say is, unlike all those other excellent presentations, you won't find any equations in what I'm presenting. So apologies for that. Doesn't mean that there aren't underpinning all this work some very strong machine learning and AI solution approaches. Thank you. Next slide, please. Okay, this is the structure of my presentation. I want to talk about the challenges and requirements in the way we tackle these problems from an industrial perspective. Example applications of AI and control. I'll go on to talk about data and its importance, which truth is you all know about. Achieving exploitation and the challenges we really face, and finally take some questions at the end. Next slide, please. Okay. So in the world that I work in, autonomous systems, they need to operate in highly difficult environments. It's not always a contested environment, but certainly it's a very dynamic and uncertain environment, whilst trying to maintain that human-machine partnership. I think it's fair to say today that we don't have any autonomous systems operating in my world. They are all managed with lots of breadcrumb trails, and we always have a human in the loop, because none of these systems have deployed autonomy functionality on them. In recent days, we've seen a greater interest in data-driven solutions to classify and let's call them targets of interest, for want of another better word, classify images, but there are no assured autonomous systems flying that I'm aware of. And maybe just my ignorance, but I don't believe that's untrue. So as I said earlier, whilst not all environments are contested, they're definitely constrained. So we can only use certain types of sensors. They are congested. They're operating, these types of systems need to operate with other crewed platforms or with other entities, a mix of air and land platforms, for example, complex environments, and very often, communications denied. So from an operations perspective, when we need to pre-plan carefully, we consider, desynced operations, where where if you're not in contact with the platform, the mission does need to carry on effectively and safely, in line with the human operator's intent, so that when comms are lost and then regained thereafter, the resyncing occurs seamlessly and quickly, and that the systems can share their respective situational awareness, and we can replan for, update those future plans, so to speak. So there's some real challenges here, getting all of these things to hand off in a trustworthy manner from one to the other. And data or information is key to achieving all of this. And we use, we are seeking to exploit machine learning and AI to enhance our autonomy and control of these types of systems. And for my work, we're really looking at those next generation systems that we want to come online. Next slide, please. So I'm going to give you some use case examples here, and this is one in particular. You're probably well aware. I don't know if you've seen that. This is the project we did for Sellafield, where they have these large football-sized storage ponds for spent fuel rods. The quote in the middle is from the New Scientist of, a few years ago. And what Sellafield, so these ponds are open to the atmosphere. You get birds coming in, swimming in there, pooping in there. In the summer, you get algae blooms. So, and over the years, the containers that contain these nuclear fuel rods have broken, and the fuel rods have fallen into the pond itself. So, you've got pretty much zero visibility in there. And our objective was to develop an unmanned ground vehicle that we could drive it, that would drive into the pond, operate in this zero visibility environment, and collect up those nuclear rods and store them back again into new containers. Quite a challenging environment, lethal levels of ionizing radiation. It says there, which blinds the sensors, scrambles integrated circuits, and prevents the recovery of the UGV ever. So we have to, it's quite a complex platform to design. Next slide, please. It was a collaborative partnership. We had Bristol Maritime Robotics, who were working on whisker type sensors. They brought their whisker technologies with us, which we mounted on the end of the arm that you saw in the previous picture, so we could feel around in the dirt to find things of interest to pick up. We had Fortis, who are a sonar development company up in Scotland. They provided us with sonar sensors, about the only thing that would work in that type of an environment. And Lancaster University, who worked with us on developing an odometry-free approach for our UGV to do simultaneous localization and mapping, so it could travel around the environment, knowing where all the obstacles were. And our job was to, in addition to building the platform, making sure the platform could cope with the environment, was to look at the systems integration, mission planning, and system integration and test. Can you play that little video by way of an example, just to show you, we did achieve all of this, but this little video is the best way to articulate. So what we did was, sorry, just before it runs, we demonstrated all of this, not in the pond itself, in order to prove that we had produced something of value. We went to Barrow Docks and we submerged our vehicle in the docks and demonstrated the art of the possible. Okay, press play, please. Okay, thank you for that. So hopefully from that, you could see some of the challenges. A highly constrained environment, very complex, very difficult to operate in, and all and the importance of machine learning and AI in enabling us to do that is pretty obvious, as indeed was the need for us to acquire data that would enable us to validate and assure the capability that we were developing, as best we could, before we attempted to submerge it in Barrow docks. And if anybody, what the docks are like anywhere in the country, I wouldn't want to drop anything in there. So yes, a very interesting project. We never did actually mount the arm and go into the Sellafield pond in the end. The customer decided that a much simpler solution of potentially using a crane across the top was perhaps more effective. They didn't want to introduce another platform in the environment. Moving on from there to the next slide, I wanted to talk about another use case, and apologies, I had a video for this, but I don't have it now, simply because it was too large to transfer. This is another project that is currently live that we are working on. It's again consists of multiple partners, a mix of universities and SMEs, where we have developed an autonomous collaborative platforms experimentation environment. It is essentially an algorithms fight club. And we are, as systems integrators, we get company A rocking up on Monday telling us they've got the best routing algorithms. And then on Tuesday, another company will come and say they've got the best routing algorithm. And for me, and for our customers, the question is which is best? And this is a 3D synthetic environment that we have built that enables us to relatively quickly, we've now got interfaces, we supply ICDs and information control documentation, information exchange requirements, so we can integrate MATLAB, C++, C, Python, you name it, Java code straight into this environment, and we can repeatedly test one algorithm against the other. So, a very successful project that we're looking to continue over the next few years. And DSTL, I need to acknowledge DSTL here. They are the main customer for this work. Move on to the next slide. And unfortunately, yeah, as I said, the video would do much more justice. It just based the center picture shows, just a number of workstations representing different aspects of the scenario that we were modeling. The particular use case was very much of I won't use the word swarm, a team of UAVs supporting a crewed platform in carrying out a number of missions. And the type of missions were they needed to travel from a meeting point and then travel from through different parts of a particular country that we generated. Actually, it was Salisbury Plain in Wiltshire in the UK, but we had power lines and forests and trees, and the question is, do you fly above the power line? Do you fly below the power line? How do you avoid the large hills, etc.? And it's quite an interesting challenge. Equally importantly, all the suppliers had to make use of real sensors, so real sensors that we could model in our SE. And exploit the sensor data to create their representation of the world, and then generate flight paths and routes for the UAVs to fly through that environment. Okay, a highly successful project, and that translates into this project. So this is the equivalent of that SE world, which is a live fly program. You might have seen this in the Telegraph at the back end of last year, sometime, where we've taken some of those technologies of interest to us, we've matured them and integrated them into real live flight platforms, and we put the controls and tasking and mission planning solution on the large jet aircraft that you can see on the top right there, an RJ regional jet platform. That's the one. Thank you. And we flew a team of those UAVs that's just there on the bottom left. in the UK, up north. So that was quite a significant, I think it might have been a European first. It was definitely a UK first, where we demonstrated the ability to task and control multiple UAVs in a safe manner on missions defined by our DSTL customer. A very, very interesting live experiment. Can I go on to my next slide? Okay, so this is a rather obvious statement to make. Across everything I've showed you, the importance of data, validation, and assurance is key. And truth is, I said a little earlier on, we don't have any real autonomous platforms flying. Even in that real fly use case that I showed you there, we have put very strict bounding boxes around it, everything that we're doing. And we are constraining the UAVs quite rigidly. So, you know, and even to achieve that, you know, how do we, the key question for us, how do we verify the machine learning systems? You know, when we struggle with having not enough real data, we don't have good mathematical models of how the data is generated when it is generated that way. I'll leave you to read all those different bullet points there, but they all relate to data and the provenance of data, ensuring we don't have bias in data. I was quite pleased to see at least two very interesting presentations in terms of safety and how we might be able to quantify or safety parameters in the papers today, because I was, you know, I've been lacking getting some direction on that. Can I go to my next slide, please? And this is the crux of where we are in terms of industry, I believe. We have no real means of assuring our autonomous systems today, where we're exploiting machine learning and AI. How do we, how do we assure those systems? Components and subsystems, may be supplied as black boxes. Again, as a systems integrator, how do I assure those systems? How can I ensure that there are no emergent properties as I integrate those third-party supplied algorithms and end up with emergent properties propagating all the way through? We have no clear regulations, standards, or governance processes. They are coming. Certainly, governance processes are coming along, and I know organizations like the BSI are looking at standards, and we are looking closely at what's coming out from there. For me, I think we've got to the page where software must be safe by design, and safety should become a through life capability, starting at the research end, collecting evidence as the most promising algorithms mature, so that we can do that safety impact on safety, and not just safety. It's about safety and security for us as well. In fact, three things. We're looking at understanding safety, security, and ethics as well. How do we quantify all those parameters? So we've got a program looking at digital test evaluation to help us understand how we can quantify safety risks within a 3D SE environment, and then qualify that against real-world test data. And then, one of the other things that's of interest to us is what metrics and measures of performance are acceptable for trust and safe operations of these types of systems. Because and maybe it's already out there, and I apologize. Hopefully one of you can direct me to it. I'd really like to see some measures of some standards applied to trust, and how we can, what's the right word here? How measures of trust can be propagated through a system, if we integrate disparate systems together. A common set of interfaces and standards for trust would be very helpful. Okay, I think I've been very quick through that. I think that was my last slide.
Thanks a lot, Hector, for this nice presentation and sharing. We have a question from Jack. Jack, yeah, you can go ahead.
Oh, great. Thanks. And thanks, Hector. Very nice presentation. On the theme of systems engineering and integrating multiple black box components, do you have an opinion on the kind of SysML v2 language that is kind of being developed at the moment? I know like a lot of people are trying to bring some more rigor to systems engineering, and SysML v2 is one approach, but do you have any industry view on that?
So SysML, as you probably know, is heavily utilized across industry. We certainly use SysML tools. And model-based systems engineering approaches are a core part of development and productization of systems. Absolutely right, and we are keen supporters of SysML.
Great.
Thank you, Jack. Any other questions for Hector? So I do have a couple of questions, Hector, more on like the relationship. I think we can start the open discussion. So thanks again to all the speakers for these nice presentations. I think it shows really how varied control theory and application is, and where are the intersection of learning AI and control theory, and what's going on in the field, and what's the link to the industry, to the industry side. My first question to you to start with, Hector, what, like, from your experience working in the industry and then with a lot of like, I think, colleagues in the field of AI, data and control, what do you think we are still lacking to make control like theory? I think it's more known in the field of industry about AI data, but a little more less about control theory, closed loop control. So to your point of view, like what are the key challenges in like taking control theory? And then you have mentioned at the beginning of your talk, open in the loop, human in the loop control. Like what do you think are the challenges that are preventing, I would say, control theory to be maybe applied in industrial settings, like the one you have shown, and where the human will be like in that loop?
So, yeah, and I hope I answer your question clearly, if I've understood it, that is. So, operating with uncrewed systems, we are dependent on the sensors. The sensors themselves are never 100%. Hey, if you're using an electro-optic sensor, you'll just get a fly that gets crushed on your lens, and suddenly you've got something including your sensing capability. And so consequently, your construction of your worldview could be impaired in some way, shape, or form. What are you seeing out there? Is that a school bus, or is that or some other vehicle, threat vehicle, for example, of some type? And so, from a control perspective, particularly the fact that, look, I did say, GPS is the ability to communicate with your platforms is never absolute. Even operating here in the UK, we lose comms, so many times. And when we lose comms, we've got to, because we're only doing experimentation, we can easily say to the platform, okay, you need to go to this reversionary point here, so we can reestablish comms with you if we lose comms with you. Now, imagine if that's in the real world out there. So it's about recognizing the fact that sensors, the sensed information is never perfect. There's a whole load of uncertainty associated with it. So our world representation is never 100%. So how do our control systems, how can we ensure that our control systems are sufficiently providing, the right kind of responses, basically, given those challenges? Did that answer the question? I'm not sure that I actually got to the core of what you asked.
Yeah, it does. Like, because usually, like, one of the key, I think, guarantees that we need as control theorists to have that safety guarantees that you have talked at the end, which is a little bit challenging. So it's very important, like when we design a controller based on sensor data for particular application, to have those guarantees, safety guarantees, which, if you think about AI or learning techniques from more computational side, most of the time, like, again, as you mentioned it at the end, it's black box. So now I think that there should be like really a link or like a deep collaboration, I would say, between learning and AI techniques, having like a black box overview, and then control theory, where we do have those convergence guarantees to converge to like a particular aim. And from the industrial point of view, like I was more like thinking about like if you have a particular project, like collaborative UAVs with particular partners, how much you have the human in your control loop, or like
so at the moment we have the human in or on the control loop 100% of the time.
Okay.
Can I give you, by way of pushing back, another problem space that interests me as well, because they're all interrelated. There's a lot of interest in the moment at this currently in terms of doing remote operations on people, where surgeons can be potentially in another country. Well, is that really achievable? My mum, who needs a knee operation, was actually offered a robot to do the knee operation for her, which I thought was fantastic, but that's locally where you've got everything tightly controlled, and you can do that type of operation locally. But if a surgeon wants to do an operation, a surgeon in the UK wants to do an operation in Africa somewhere, how do we manage the control around something like that, where you might have a latency in communication, a lag in communication? There might, if there's a drop in comms at any instance in time, what happens? How do we address those types of challenges? It's a different use case, but for me it brings all the same challenges that we experience with flying UAVs or UGVs or whatever, and they're all of interest.
Yeah, I agree. Yeah, that's a good point and good application, Hector. So any other questions maybe to Hector on so the idea of this open discussion, it's really like because I think we rushed like over the question in some sessions, like to ask your question to our speakers who are still with us, like some had to leave for teaching, but others are still with us. So yeah, if you can ask your questions to those speakers, and then we will open like the discussion there. Jack, yeah, go ahead.
I was going to ask another question to Hector, if I may.
Please.
So I guess at some point in the presentation, you mentioned kind of certificates, and you were eager to maybe understand from the research community what certificates and guarantees are available. But maybe to flip the question a bit, we can also ask you, as a practicing systems engineer, what kind of certificates and what kind of guarantees would actually convince you? Because I mean, we know that we can make some polynomial approximations, do some sums of squares, but what are the kind of certificates that would actually convince you before you deploy that expensive, safety critical mission?
So thank you. So we say if we really have real problems in this space, if it's an air platform, then the Civil Aviation Authority, demands, in my view, no, as I understand it, certainly demands higher levels of certification or safety, higher levels of safety than performance of these systems than we might do for a pilot flying something. Genuinely do, that's a fact. So there are approaches. The approach we take is you're familiar with the goal structured notation approach, perhaps, where you basically you make a safety claim about how you're going to address a particular safety problem. You make a safety claim. You have a whole bunch of arguments that back up your safety claim, and then beneath that you collect evidence that supports your arguments, basically. And that is the kind of approach that certainly a number of regulatory authorities take to show that you have truly thought about a particular safety case, and you have the evidence to say, okay, this is safe or only safe under these conditions. And so consequently, that's the kind of approach that we apply when it comes to safety. and the approach that we are also looking we apply for security as well. What we're seeking to do at QinetiQ is to take that entire approach to embed it in a synthetic environment and design a whole bunch of tests where we can perturb the SE environment, whether it's inputting weather perturbations, noise, to obscure basically sensor noise. And what does that mean for the safety parameters that somebody has stated is required for a particular mission, for example. That's the kind of approach we're trying to take. To understanding safety for autonomous systems, to see if we can apply it across the board. I was really interested in unfortunately I missed the start of the talk, and I missed Professor Kostas, is it? No, Kostas is that his first name? Kostas's presentation. And I wanted to ask him a question for, if he's still on,
I'm still here, so you can go ahead, Hector.
Yeah, no, really interesting presentation. I'm really interested in understanding whether we can apply your approach to generating the safety cases, and more importantly, getting quantified estimates for understanding how we can quantify those safety cases, and what kind of evidence we might need to collect I'd like to put in front of our civil aviation authorities to say, here's an approach that we are pursuing, after kind of articulated by you, and what their thoughts are with respect to that type of approach for saying a system is safe.
Our take on this was that we accept a small probability of the system of our certificate about the system being false, and we try to quantify beforehand how small this inability to make a statement can be, simply because we rely on data, and sometimes we may have misrepresentative data. So we want this we have an a priori quantified level of a false design, which hopefully is very small. And then the other thing that we thought would be interesting, or at least our take on safety, was we don't want to split data between training and validation data, but we want with a single data set to train and validate if you want at the same time. So an appealing feature, we believe, of our approach would be that we have a fixed pool of data. We use everything to make a design, to build a certificate, and at the same time quantify the risk associated with the statement that we are doing. So we don't split data sets between training and validation, which we feel might be helpful in terms of exploiting the data that are available.
No, that's very
I will send you an email with the paper. So
thank you very much. I definitely need to follow up on your approach.
Yeah, likewise, we'd be very keen to scale it up. So we're trying now to see what the limits of this are. So any feedback is welcome.
Thanks, Hector and Kostas. This is hopefully one of the aims is to start new collaborations as part of this ACE network and those workshops. Maybe a more general questions to all our speakers who are with us. So again, this is our first workshop to foster collaboration, and I'm very keen to hear your thoughts. Like you have presented different application. Francesca talks about energy management using control theory, as well as Jack, for example, he was talking about this application using another techniques. So what do you think, what are really the types of collaboration that would be beneficial the most to control theorists or people from more AI or computer science and people from the industry? So what types of collaboration you think we need to foster more as part of this ACE network to have more collaboration? So This is more to the speakers. I'm really keen to understand or to hear from you so that we can plan effectively for our next workshops and then events. Anyone wants to jump here?
Can I jump in?
Yeah, go ahead, Hector.
So I think we've got fantastic researchers. I mean, from what I've seen today, some of those presentations were brilliant. It's really unfortunate, in my view, that we have very few what's the right choice of words here? Let me call them programs of record that exploit the research, the wonderful research that you do. We have insufficient opportunities. A lot of this, we do fantastic research, and then it stops. A wonderful paper published, and I kind of feel it doesn't seem to go very far. And I think we need those exploitation programs of record that of sufficient funding that enables us to integrate and apply those excellent presentations that I saw today, so that we can truly see which ones are. I mean, some of them may well fall by the wayside, but certainly the best ones, will go forward, and we much more quickly end up with a product that'll benefit, provide you with a return on your investment and your IP, and enable us, to turn into bigger systems and capability. So I think there's something missing there, but maybe others have a different view.
Yeah, thanks, Hector. Any others? Thoughts from?
Maybe I can share a couple of thoughts. So I think that okay, to structure my thought in a better way, I felt that it is important to think about the academic transition that needs to happen to facilitate this, and the industrial one. So Hector argued a bit about the transition from academia to industry, so that something doesn't stop in a research paper, and I fully agree with this. And in part, this idea of the network to create a portfolio of synergies and proposals is trying to work towards that direction. In terms of academic approach, I feel that if we talk about data and AI, there are a lot of success stories and a lot of momentum from computer scientists and people from machine learning that come with slightly different backgrounds. And as a control community, I think we need to embrace and engage with them to achieve that transition. When people hear about data and AI, I don't believe they necessarily think about control, even if very often we deal with similar problems. I believe it has happened in the past where people were working, for example, there was a huge era of hybrid systems, later on cyber-physical systems, and there were people that were approaching the problem both from the computer science and the control theory angle. I believe that the same thing is happening right now with data and data-driven control, optimization, decision-making in general. So I believe there should be a stronger synergy with computer science to avoid reinventing the wheel and try to also strengthen the output that we have as a community in that domain.
Yeah, makes sense. Yeah, Francesca, I saw your hand. Yeah, and thanks, Kostas, for your shared thoughts.
Yeah, I agree with what has been said already. One thing to add, and sometimes I find challenging, especially from a control perspective, is to find collaborations with the industry, because sometimes there is a bit of a struggle to get real world data, to get specific real world problems, especially if we are talking about safety. I don't know if it is just what the experience, but of course there is a bit of resistance in sharing these, sharing problems. I understand, of course, the reasons. There might be sometimes problems related to confidentiality. There might be problems related to security. But I think that really, in order to get the most from the research that we are doing in the control environment, in the control theory environment, I think that being able to share more these needs that come from industry, from the real world, would help to focus our research in the really important challenges. That's a bit my experience. Of course, it might not be true in all the industry fields, but I found a bit of challenges in especially in the safety area, being able to know what are the real problems, what are the risks. Yeah.
Thanks a lot, Francesca. Yeah, I do agree like a lot with this point. Like it's always very hard to get in touch with industry partners and know about the problem. But yeah, we are hoping maybe to have some more workshops just with industrial partners. So one thing we are doing here, like it's on different application, it's more on healthcare application. So we are organizing what we call like clinician meet engineers, like all engineers or control engineers, where we have both parties in the same room, and then like the clinician will talk to us about their problems that they are facing, and us engineers will talk about the methods we have, and then we try to find a ground truth. I think this is the kind of workshop, like maybe it will be beneficial to the control like theory community, where like we have some industrial partners and then some control theorists or control researchers in the same room. We will hear from them like the problems, like Hector mentioned safety, it's very important to them. And we can help as control theorists in that field. I think this is one of like the ideas kind of workshops have in mind to maybe put forward as this ACE network to promote more interaction, collaboration, discussion between industrial partners and control theorists. So that's really, like, I think an important point to move forward. Yeah, Jake.
Yeah, maybe I can say something that kind of brings together what Hector, Francesca, and Kostas have been saying. So I definitely agree 100% of what Francesca said about the need for real industry problems to shape research. I also thought it was interesting when Hector was presenting this kind of large simulation environment. I wonder if this can be kind of made available to the research community so that we can kind of benchmark our algorithms on something that is kind of industry standard that would convince people that Hector works with, which also kind of relates to Kostas' points about the CS community, where I think a lot of the progress we've seen in CS and machine learning has been because of benchmarks, right? In computer vision, it was mostly driven by massive data sets where it was very clear what progress was being made, what was working, what wasn't. Same with reinforcement learning, with very clear benchmark problems, whether it's OpenAI's Gym or even games like Go or whatever. So I think that would really help both aspects, right? Focus our problems, but also allow us to actually see which solutions are making progress on those problems.
Thanks, Jack. Yeah, I think that's really a good gathering point between the three. So I know like we are 2 minutes, like maybe my last, before concluding, we had a couple of questions from like participant Mohammed Boukaf. I think some of your questions, unfortunately we didn't have time to address them. I think we have 3 minutes now. Like Mohammed, if you can ask your questions directly.
Yeah, good morning, everybody.
Yeah,
I don't know if you can hear me or not.
We can hear you, yeah.
Yeah, perfect. So I wanted to ask you a question, Professor Kostas, about like uncertainties and like noisy cases when you have like data and you have like this frontiers maybe between the unsafe and safe zone. How does it like impact your probability estimation and the confidence? I mean, I don't see in which like specific part it would impact, if you can like just clear me about that.
Yeah, so I try to answer in the chat, but it's the way that I understand the question at least, right? So let me paraphrase it a bit. So you're saying that in my talk, uncertainty was pretty much lack of knowledge of the system, and we only had data about the dynamics of our plan. Now you're saying that the actual environment is also uncertain, so you may have noise even in the definition of the different domains that we have in the system.
Yeah,
for
exactly.
example, the uncertain or the unsafe or the safe domain. In that case, I would say you can apply the same theory, but the guarantees would refer to the joint probability distribution that governs the uncertain dynamics, so the one that I indicate as P in my talk, and the distribution of the noise that results in uncertain, safe or unsafe regions. So the guarantees will refer to that joint object, which will be, if you want, a multivariate distribution capturing both sources of uncertainty in the system. The only difficulty with that, even though mathematically I believe this would be well defined, is the interpretability of the result. Because right now you would have, if you follow that path, you would have guarantees that either your design is false because your certificate is not good, your certificate stops being valid, or because the noise level is too high, if I put it in very loose terms. So how to interpret the final result would require some extra work, and I think this is not entirely clear to me. But I would start from that path.
All right, thank you very much. I also had like one small other question regarding like the trade-off between the risk and the confidence level. Like, how do you manage this trade-off? Like, I saw that you gave more importance to the confidence than to the risk in your presentation. Can you elaborate on that, please?
We don't give more importance to the confidence. I just think that naturally in there are three parameters, and the bounds that we try to identify depend on effectively all three of them. So what I mean is the complexity of the problem, which is manifested in this compression cardinality of the data, the confidence, and the number of data that you have available. So depending on the application, you have to fix one of the three. The way that I presented it, motivated by the applications that we've looked at, we want to make statements with very high confidence, very high trust. That's why I was fixing the confidence to a very high value. But if you believe that you can get away with fewer confidence and you want to find how much data you need, so you need to find the extent of data that you need to use to solve your training/generalization problem, you could follow a different path. So there's a common function that joins all three parameters.
Thank you very much, Professor.
Cheers.
Thanks a lot. I think with that final question, we are ready to close. We are on time. So let me reiterate my thanks really to all the speakers who made this event happening today. And it's not the end, like it's just the first workshop, and really looking forward to, again, follow-up workshops, collaboration events, maybe industrial events, and are thinking of having maybe kind of sandpit. So please keep tuned with the ACE network and the announcement. And I really hope to see most of you in our upcoming events. So thanks to the participants for your interaction. And I will tell you, like, see you next time. Thank you, everyone, for joining us today.
Thank you, everyone. Thanks, Zehor, for sharing that.
Thanks a lot, Kostas.
Cheers. Bye-bye.
Thank you. Thank you to everyone.
Thank you, everyone. Bye-bye.